So the plan today is to start some work on chapter 14. So this will be the last of the material that we talk about this semester. I know your cameras are off, so I can't see all of your crying eyes, but we are getting down to the end of this semester. So chapter 14 deals with cardinality of sets. So this is something we have thought about, at least informally. So I want to think about this more formally. And as far as the plan for next week goes, we don't have anything next week. You have Thanksgiving break, so that's the plan for next week. And then we just have 1 week after the break. So when we come back after the break, we'll wrap up this material on Monday, I think. Your homework is due on Wednesday, and so on Wednesday's class, we might just have a couple of loose ends to tie up, and then we can just talk about the last exam, which is on Monday of finals week. So just keep that in mind. Any questions before we get started? I also just want to point out that I put links to the FCQs, the course evaluations, up in Canvas. So if you haven't done so, please do take a few minutes to give us your thoughts about the course, about all of your courses. Okay.
I have a question.
Yeah, sure.
On Monday after break, will we have a pre-class quiz?
I'm not going to have any pre-class quizzes next week.
By next week, you mean the last week of class?
Yeah, last week of
class. Okay, thank you.
And not over Thanksgiving break either, yes. Okay, anything else? Okay, so then for the reading for today, you guys did some reading about cardinality, finite sense, infinite sets, what it means to be countable maybe to some extent. So I want to just kind of start with a little activity. So here are 10 different sets that are listed out. And I just like you, based on whatever you think is the correct ordering, order these things from smallest to largest in terms of cardinality. And so I have a poll that is open. I think if you click on that link, you should be able to get there. Let me switch over to that. Here it is. Yeah, so here's kind of the poll. You can get to it at the link above, which is also given on the sheet. So it's just a bunch of sets. I don't know why they're formatting. I guess they don't like math formatting. Why some of them are big, some of them are small. I guess they needed to fit them all on the same line. But just kind of order these things from biggest to smallest. I'm guessing that you have a way of dragging them around when you open this up. Are you able to see the poll? Yes, no?
Yeah, you can see it.
Okay, thank you. I can't see if it's working yet and without closing this up. So if you're having any problems, please just let me know, chat them in. Otherwise, I'll assume that it's working. And so since I can't see the progress, once you're done, you mind just like hitting the chat and just letting me know that I'm done, that I can see. Oh. I did absolutely nothing. Did you guys see that? Okay, well, I guess the results are in. Did everybody get a chance to submit? Oh, I guess it's updating as people are submitting. Then you shouldn't look while it's submitting. I don't know how to change that. Anyway, don't be swayed by what other people are saying. I see.
I just realized it says smallest to largest. I don't know if I can change my answers.
That's okay. We'll see the anomaly. Okay, so please let me know as you are finished, just so I know when to share this. Jeez. Okay, so I can, by the chat, I'm guessing 2 people have finished. Has anybody, are you guys still working? It's not a quiz, just kind of whatever you think off the top of your head. Just kind of, this is supposed to be a fast sort of thing. Awesome, thank you. Okay, I think I'm getting some responses in. Great, thank you everyone. Okay, so here's the responses, at least so far, and there might have been some misinterpreting smallest to largest in terms of largest to smallest. Yeah, so I would agree that the very first one, the first 100 natural numbers, that would be the smallest out of all of these. That is the only one that has a finite number of elements. So yes, that is certainly the smallest. All of these other sets actually have infinite number of elements. And so the idea is, well, how can we order things that, are there different orders or different magnitudes of infinity? For example, the natural numbers compared to the integers and things like this. So let's jump back into this worksheet. Sorry, I don't know how my technology skills compare to your average college instructor, but doing the best I can with Zoom. Okay, so here's our worksheet. And so out of these, yeah, so this one is finite over here. All of these others are infinite. And let me just say, what we'll work on today is kind of seeing which of these infinities are the same and which ones might be bigger than the other. So the number of natural numbers is exactly the same as the number of integers, which is exactly the same as the number of irrational numbers, which is the same as this and this and this. So actually, all of these things that I just boxed in red all have the same number of elements in them. And there are some exceptions, which is this one, this one, this one. These are all also the same magnitude of infinity, which is larger than the ones in red. So this is what we'll kind of try and clear up. So the things that I boxed in red, these are what would be called countable infinities. So although there's an infinite number of things, we can count them in some sense, whereas the ones that are in green, these are all uncountable infinities. And so that will be kind of the focus of what we talk about on Monday after the break, would be these uncountable things. So today I want to focus on the countable side of things. For finite things, it's not all that interesting or complicated, but for these different infinities, it's not that easy. So I want to focus on how we can identify whether something is countably infinite. But any questions about this? You might be wondering, why is the real numbers bigger or less than these others? That I need to convince you of. But any questions about the finite versus infinite, I guess, is the main thing right now. Okay, so on the video or the reading that you did for today, we kind of talked about how if we're trying to show that two sets have the same cardinality, we don't just want to say we can count the same number of things in this set as we can in this set, because we want our definition to extend to infinite sets as well. So instead, we're going to define two sets have the same cardinality if there is a bijection from A to B. So remember, that means injective and surjective. So the kind of general picture for these that you generally see are, okay, here's set A, and it has a number of elements, column A, B, C, D, E, and F, and then we have some other set B, and maybe it has some elements. And as long as we can come up with a map that takes every element from A, I counted wrong, to its own unique element in B. Oh, wow. There's a big lag here. Just wait, you're going to be amazed. All right. So that we can map, there we go, each element from A to exactly one element in B. And I do think I left something off here. I'm missing one. We're going to call this one 6. Okay, these don't need to be in order here. So each element in A is getting mapped to exactly one element in B, and we're hitting every single element in B. Then we have, we would say that A and B have the same cardinality. Okay, so that's going to be the name of the game for finding whether or not two sets have cardinality. It's going to be, can we define a bijective function that maps from one set to the other? And that's what we just spent a whole bunch of time talking about the last couple of classes. How can we identify bijective functions? Okay, so we say that a set is countably infinite if it has the same number of things as the natural numbers. Okay, so we think about the natural numbers as things that we can count, 1, 2, 3, 4, 5, 6. So if I can find a function which maps from the natural numbers into my set A, which is a bijection, then we say that set A is countably infinite. And we use this letter. This is a Hebrew letter, Aleph. It's the first letter in the Hebrew alphabet with a subscript of 0. So this would mean like the smallest of various infinities. So countably infinite is kind of like the smallest of the infinities that we'll encounter. So we would say that natural numbers have a cardinality which is equal to Aleph sub 0. So we would say the cardinality of the natural numbers, we wouldn't say is infinity, we would say that it's Aleph sub 0. And so we say that sets are countable if they either have a finite number of things or if they are countably infinite, meaning they have the same number of things as the natural numbers. So countably infinite means same amount of things as the natural numbers. So the whole idea of is some set that has an infinite number of elements countably infinite, or is it uncountable, all falls down to whether there exists a bijection from n to the set. And if we can prove that there is a bijection, then that's a proof that the set is countable, countably infinite. If we can show that there does not exist such a function, then we've just identified that this set has more things than the natural numbers. So these proofs show that this set is countably infinite, again, is really boiling down to, we want to show that, there exists a bijection from the natural numbers to this set. So let's take the first case to be the natural numbers. Okay, so I'm going to claim that that is countably infinite. And my proof is going to be, here's a function which maps from the natural numbers into my set. So it's all kind of using this definition up here, where now our set A happens to be the natural numbers. So what is a bijective function that you can think of that's going to map the natural numbers into the natural numbers?
F of x equals x.
Yeah, let's use the identity map. So sometimes when we write out these functions, just keep in mind that sometimes we, rather than use like f of x notation, we might use this arrow, which says that this element maps to that element. Okay, and so that's just another way of saying that my map is going to be f of a equals a. And I think we're all convinced that that's injective and surjective, right? Since what goes in is exactly what comes out, different things get mapped to different outputs, and we're going to be able to hit every single thing in the codomain. Okay, so this would be a really big problem if the natural numbers themselves were not countably infinite. Okay, and so for other sets, it gets a little bit trickier. But any questions about that one? So next, we want to think about the even numbers. And kind of here's the complicated thing maybe about infinities, maybe not complicated, but counterintuitive, which is the even numbers, even natural numbers, I should say, is what E is representing, is a proper subset of the natural numbers. Right? There are certainly elements in the natural numbers, 1, 3, 5, etc., that are not in E. Okay, but what's interesting is the actual number of things in set E are the same as the number of things in set N. So what these things look like I'm not going to list them all. We'll be here a long time. But we have all of our natural numbers over here. And now we've got this other set of even natural numbers. Yep, and what I'd like to find is some injective map from N into E.
Maybe f of a equals 2a.
Yeah, exactly. So we can define a map where for each natural number N, we map it to 2N. And we would just want to verify that this is indeed bijection. So we'd want to just verify that if M and N are not equal to each other, then 2M is not equal to 2N. That's pretty quick there, as well as we'd want to verify that for any element in E, there is some element in N that maps to it. Yes, just pick 1/2 of whatever the element in E is, and that's the element that will map to it. So here you could certainly prove that this is bijective. So these proofs would just be and I'll just say the kind of detail that we left out here is that we would want to just prove that F is bijective, again, by saying here's a proof for injectivity, here's a proof of surjectivity. I won't get into those details here, but that's the idea. So sometimes we can actually construct a map like we did here explicitly, and sometimes the best that we can do is just say that we can show that some map exists, and maybe we can't define it explicitly, but either way of doing it would be fine. Any questions? Okay, so E is a subset of the natural numbers. However, they have the same number of elements. No one seems to complain about that. Okay. It took me a long time to accept that myself. I did not like that. Okay, so next, let's think about the integers Z. So now, right, we still are going to map from N over here into Z. And so now we've got a problem because right, these integers, gosh, that's bad, kind of go off in both directions. Whereas the natural numbers, they're only heading off towards infinity in one direction. So we want to come up with a bijection and we can. So Z actually has the same number of elements as the natural numbers. Anyone think of a way that we can define this map?
With the square root function?
So the square root function is, I mean, like take the square root of this thing to get over there.
Yeah, because there's going to be a positive and negative solution. Well, not for all.
We'll have some problems because things like the square root of 2, right, wouldn't have anywhere to go in the integers. So we want to make sure that we're mapping only to things in the integers. Not a bad idea. And it also has to be a function, so you want to be careful. I can't say, let's take 1 and let's map it to +1 and -1 at the same time, right? Each thing only can go to one element, and it should only go to one element. So let's kind of think about how we might define this. I'm going to call this function f. So I'm going to pick f of 1 to map to 0. So there we've mapped 1 over to 0. Where do you want f of 2 to go? All right, I'll be the boss then. I'm going to map that to 1 just because it's the next nice number. So now we've got, sorry, a highlighter 2 going over to 1. Okay, and I saw that some suggestions are coming in here. So not a bad suggestion, Brandon. Thanks for that. Yeah, so there might be some idea here that I don't just want to make f of 3, 2, and so on, because we're going to miss all of the negative numbers, right? So I don't just want to move down. Let's make sure that we hit these negative values. So I'm going to put f of 3 to be -1. And now that gives us eek. That goes over to there. And now we can take f of 4 and let's map that to 2. Ugh. Okay, so we got one. Sorry, we started off with f of 1 in the one shaded over here, and we're going to map that over to 0. Then I'm going to take the next natural number 2 and map it to 1. Then I take the next natural number 3, make sure I'm also hitting the negative values. And then take the next natural number 4, going to map that over to 2. And now we've got a pattern going here. I can take 5, map that to -2. And so on. And so kind of the next one, 6 would go to 3, and 7 would go to -3, and so on, and so on, and so on. So let's try and define this function. I'll call it h of n. We can actually write a formula for this function. We'll just define it whether it's even or whether it's odd. So if n is even, okay, n is the input that we have over here, by the way. So n is what goes in. So if n is even, that's like this one and this one, and that would have been the next one if we had drawn it. What seems to be happening with the even number? I take 2, I map it to 1. I take 4, I map it to 2. I take 6, I map it to 3. So how could we write a formula for that?
We're dividing it in half.
Yeah. So if n is even, then we're just going to take it and divide it by 2. Yes, thank you. And because n is even, we get an integer, right? We don't have to worry about getting something which is not an integer.
What about 0 then?
Yeah, so here we're referring to, n is referring to this. And so that would mean we've taken into account where does 2 go, where does 4 go, where does 6 go, and now we need to think about what happens, how does it work on the odd ones?
I see.
Yeah, so we do need to get 0 out of here, but 0, we're going to get 0 from mapping one of the odd numbers over. So we'll have to make sure that works over here. Yeah. But now we do have these other odd ones to think about. And what's a formula for those?
Can we do 1 minus n over 2?
Yeah, just about. I think you want, yeah, you're right, sorry. We want, that's it. We want n minus 1 over 2. Yeah. That would work. So for example, when n is 1, that's why we get 0, right? And when n was 3,
I think you have to do it.
we want to get negative numbers out of here. Yeah, I think you're right. So if we do it like that, then when n is 1, we get 0. When n is 3, we're getting -1. When n is 5, we're getting -2, and so on. So that one works out. So basically, we're taking the even numbers, we're using all of the even natural numbers to map to the positive ones. We're using all of the odd natural numbers to map to 0 and the negative ones. So here's our map h of n, and you would want to check that this is injective, surjective, and thus it's bijective. And that means now that I have a map from n into the integers, we're good to go, right? We've got our bijection. Okay, so far what we've seen, we have proper subsets that we have kind of the even natural numbers are properly contained inside of the natural numbers, which are properly contained inside of the integers, yet all of these things have the same number of elements in them, something which is the same as the number of natural numbers. So all of these sets over here we just proved are countably infinite. Okay, any questions? Okay. So I'm going to give you some time just to bounce some ideas off of each other about 4, which should be a little bit more direct, and 5, which is going to be totally open-ended for you. So I'll say that in 4 and 5, both of those sets are also countably infinite. So for example, you can find a function f, that's not the way I want to do it, which maps from the natural numbers we can find some map which maps from n into n cross n, which is a bijection. And so you actually can't write out a formula for that function. So I'm not looking for a formula, but maybe just looking for you guys to think about some ways that you might be able to consider that bijection. So I'm going to break you up into breakout groups. Definitely focus on 4, make sure you're comfortable with that one. And then think about 5 with each other. Just I'm not expecting you guys to solve it, but maybe just come up with some ideas that we might want to consider that, and we'll work through it together. But I want to give you a chance to talk to some of your classmates about this. Any questions? All right, so the rooms are open. So start with 4 and then just see how far you can get thinking about 5. Okay, so seems like question 4 was okay with the groups that I checked in with. Was that the same with the group that you checked in with, Nat? Was question 4 go okay?
Yeah, question
Yeah.
go.
Okay. Yeah, so like, for example, the map n goes to n plus 1 would do the trick for that one. Yeah, so now let's think about this one. And let me just say that when we're coming up with these maps, like we did back, where'd that one go? There was one that was nice and color, this one over here. So when we had these maps over here, we showed that there's a map from n into the integers. And another way of saying that a function is countably infinite would be if we can list them in an order, where basically what we're saying is, this is going to be the first element, the second element, the third element, fourth element, fifth element, and the sixth element. So like another less counterintuitive way for this one could have been, this is my first element, and then this is my second element, that's my third element, that's my fourth element, that's my fifth element. And we could say, well, we could just keep bouncing back and forth and back and forth. And by doing this, we can count up all of the integers. This would have been another way that we could have argued it that would have been just as good as actually writing out a formula as we did over here. So as long as we can list out all of the elements in an order, then that's going to be enough to show that the set is countably infinite. So I'm going to pick this to be my first element. So I'm going to call this f of 1. So 1 goes over to here. then I'm going to take 2. I don't know. I can pick whatever I want. I'm going to take 2 and map it over here. That takes care of this one. And then I can take 3 and map it over to here. And so what I'm going to do here is just kind of snake my way through all of these. So I'm going to start here, and then I'm going to do everything on that diagonal. Then I'm going to come down to the next diagonal and then order all of those. And then I'm going to come over to the next diagonal and order all of them. And if I keep on doing this out forever, I'm going to be able to order every single pair of natural numbers. So I'm just going to say, this is the first one. This is the second one. That's the third one. 4, 5, 6, 7, 8, 9, 10, 11, and so on. So I don't have a formula that says take 1 and map it to this that I have an explicit formula for, but I can show that 1 exists. If I do this process, I will be able to account for every single ordered pair in NN. So it's just as long as we can find some way of ordering and counting all of these elements, that's going to be enough to show that there is a bijection. So although I didn't find a formula, here's a map. We're going to hit everything over here, and each of these numbers is only being mapped to one of these ordered pairs over here. So n cross n is countably infinite. And I'll say that there is a theorem in the book that says that if you have 2 countable sets and then you take the Cartesian product of them, that result is also going to be countable. Maybe we can take a look at this next time if you like to prove that more generally. But here's one application of it for the natural numbers. Okay, any questions?
Did you say that there was a proof for that, or that it was a theorem?
For this guy over here?
Yeah, for the Cartesian product of 2 countable.
Yeah, there's a proof for it. We can take a look at this next time. The textbook actually does one by like a whole bunch. So they say that if you have if
Does it do it by
A1 through A,
induction?
yeah, they say if A1 through AN are each individually countable, then the Cartesian product of all of them is countable. So they do this in the textbook, and basically what I just claimed over here is the base case for that proof. So this would be like the base case, and then you could extend this out using induction. The inductive step is actually the easier part of that proof. Proving the base case would be this theorem over here.
Cool,
But
thanks.
yeah, let's put that on the back burner for next time. I think that definitely is something worth taking a look at. The goal here is to try and work our way to the conclusion that there are the same number of natural numbers as there are rational numbers, Q. So we've shown that there are the same number of integers as natural numbers. And what I'd like to do is get to 7 and convince you that there's the same number of natural numbers as rational numbers. And we've got a bunch of that proof thought about in 5. So now if I want to change this to positive rational numbers, I can think of these positive rational numbers as ordered pair, A over B. Right? So I can almost think about this as like a Cartesian product of something. Where we're just going to restrict ourselves to A and B. Their ratio is positive. We're only thinking about positive rational constants. And so for example, we can think of like 1 as 1 over 1, and thus we can think of 1 as the order pair 1, 1. And so what's the difference between what's being asked in 6 and what we did in 5?
It's really not much different.
It's not much different, but there is some difference, right?
We have B can take on a lot more values.
Yeah, like we have this notion of reducing fractions, right? So in some sense, if I'm thinking about these ordered pairs as rational numbers by taking the first one, dividing by the second one, then 1, 1, and 2, 2, and 3, 3, and 4, 4, they're like all the same number, right? So we can just define this map. Actually, Q plus is a smaller subset than the one that we had in 5. So I can just define this map now to say, well, we had f of 1, that went to 1, 1. We don't need to change that. And then I said f of 2, well, that goes to 2, 1. And that's fine. And we can keep on going. I said that f of 3 was equal to 1, 2. So far, right, as rational numbers, these are all the same. Or excuse me, they're all different. And then I'm going to say f of 4 is going to go down to the diagonal 3, 1. That's also a different number. Say f of 5. I'm now like working my way across this diagonal over here. So I said 1, 2, 3, I'm at 4. Here I am at 5. But we've already done that one, right? So we don't want to count that one again, so we just skip. So I'm not going to define f of 5 as 2, 2. I'm going to go to the next one. Oh, sorry, the next one was 1, 3. And that one we haven't hit yet. And if I keep going in this process, right, hopefully I've convinced you that we will hit every positive rational number. It's just that when I reach a pair of natural numbers that is already equivalent to one of the rational numbers we've already accounted for, we just skip it. And so I'm not going to let f of 5 equal that because I want this to be injective. And so I don't want two different numbers, 1 and 5, to get mapped to the same thing. So we just avoid that issue by saying we've already hit it. We don't need to define f of 5 that way. We'll let f of 5 be the next rational number that we haven't already counted yet. Okay, any questions about that? So now we've got things like the even numbers. These were inside of the natural numbers that are inside of these things that are inside of this thing. So these are all kind of subsets that are embedded in each other, but they all have the same number of elements, meaning we can count the number of elements in them. So when it comes down to Q in 7, what do you think we can do for this one?
Same thing, but we're going to go in both directions.
Yeah, so now we want to, first of all, we want to be sure that we have 0 in there, which was excluded, and then we'd want some negative things. I'll just say it's going to be pretty similar to the process that we did over here, where we kind of said, okay, if we're going to define it one way if n is even, and another way if n is odd. And this was a way of letting us get, for odd things, we got the negative values, and for even things, we accounted for all of the positive values over here. So we can kind of do the same thing over here. We've already counted up and said that we can count the positive ones. And so now really all I need to do is we know that there is a bijection from n to q plus. So from 6, we saw that there is some bijection f that maps from the natural numbers to the positive q's. And so now what I want to say is, well, can we somehow now come up with a bijection from q plus to q, and then we can just define our bijection from n to q by saying, first we do f, and then we do g, right? We could compose those two functions together. So let's just define this map G in the following way. Oh, sorry. So let's let kind of I'm going to let this map K be the composition of F and then G. So this is going to map from N ultimately over to Q, right? With this kind of stopover at Q plus in between. So we're going to define this where now N is coming from the natural numbers because K is going from N into Q. And we'll just kind of define this in different ways. We need a special case here in the sense that I want to be sure that I count 0. Okay, so now we're not just going to the positive rationals, but we want to go to all rationals. So I'm just going to say my first map is going to take the natural number n, and that's going to map to 0. Then I'm going to take 2, which is this even number, and I'm going to map this one to f of n over 2. So basically, all of the even numbers are going to count up all of these. So 2 is going to map to this one, 4 is going to map to this one, 6 is going to map to this one. So I'm going to use all of the even natural numbers to map to all of the positive rational numbers, which we did over here already. And then I'll use all of the odd ones to map to all of the negative rational numbers. So it's kind of a takeoff of what we did when we went from the natural numbers to all of the integers. In fact, yeah, I really don't even need the top line, right? Because n equals 1 would give me exactly 0. But And this gives us a map, a bijection from the natural numbers over into Q.
So does this,
Sorry?
does this
Sorry?
give you things like if you were trying to get 1/3, let's say, how are you getting 1/3 from this?
So 1/3 was f of 5, according to this, right? How I counted it. So I could get 1/3 by taking, according to this, k of 10 would give me f of 5, and that is 1/3.
Okay, I see it now.
Yeah, and then we could say like k of 9, well, that would equal, oh, I see. I kind of did that. Let's kind of be careful about this. So this would give me f of, let me do it like this. Yeah, sorry. I see I made a mistake here. I want to get negative rational numbers out of this. So I need to put a negative sign outside of there. So like k of 9 is telling me I would get minus f of, since 9 is negative, I would get minus f of 9 minus 1 over 2, which would be minus f of 4. And that would give me, for example, minus 3. And if you're like, well, what if we wanted to get minus 1/3? Well, that's what k of 11 would do. That would be minus f of 5. And so that's how I get the -1. So it's like one of them is going to give me the positive one, and then the very next one's going to give me the negative of that. And then I get the next rational number, and then I get the negative version of that. And then the next rational number, and then the negative version of that. Okay, so that's one way to do it. I think the textbook proves this in a slightly different way. Actually, I think they use like a snake lemma for that. But we'll pick up from this after the break. And what's left to do is to show you like why we can't do this with the real numbers. What happens when we have irrational numbers and things like that. So we kind of have reached the end of our countable infinities, and now these larger sets that we want to think of, once we incorporate irrational numbers, we're going to get things that are uncountable. And so how can we prove that something can't be counted? That's going to be a contradiction proof for those. Okay, well, enjoy your Thanksgiving breaks. You've all earned it. I've got office hours tomorrow, 10:30 to 11:30. If you've got any questions, I'll certainly be around. Not going anywhere. No one's going anywhere. So if you have any questions over the break, I will certainly be around. You should be able to get going on a good portion of your homework over the break. But otherwise, I'll see you guys on Monday after the break. Have a nice Thanksgiving, everyone.